Laws. Kepler's first law is that orbits are elliptical. Kepler's second law is that in equal time intervals, areas of the intervals between the planet and the sun are equal. So let me draw that. Here's the elliptical orbit. And then here is the time interval. Say it's like 3 days. So here's 3 days. And then here's 3 days on the other side of the orbit. So you see, the planet moves a smaller distance on the farther side of the orbit than on the closer side, but the areas in between the intervals are equal. This is equal to this. The third law is that the period squared is proportional to the semi-major axis cubed. The semi-major axis is this. So that is A. The period is the time it takes for one orbit squared, so that's T, the time around the whole circle.
Newton proposed that any two masses are attracted to each other by a gravitational force. So F of g, which is the force of gravity, equals negative g, which is the gravitational constant 6.67 times 10 to the negative 11, times the first mass, which is big M, times the second mass, all over r squared. And r is the distance between both masses.
Okay, so you have to start out with the same energies, initial and final, and then you have the kinetic energy and the potential energy. It's not MGH because it's a gravitational, universal gravitational. And so this whole big thing, you can simplify down to this, and then with further simplification, you can isolate the velocity, and then escape velocity is just going to be the square root of 2 times the gravitational constant times the mass over a radius.
Alright, so we're going to try and find the escape velocity on Uranus. So the escape velocity is given by the square root of 2 times the gravitational constant, which is 6.673 times 10 to the negative 11th times the mass of Uranus, which is 8.681 times 10 to the 25th. And that's all divided by the radius of Uranus, which is 25,362 kilometers. And that will give us 21.3 kilometers per second for the escape velocity.